Hello, Mr. Maestas here, and welcome to the video. Today I'm going to talk about graphing linear inequalities. So I'm going to do two examples of graphing linear inequalities and see if I can make some sense out of some of this. First thing I want to talk about, a couple things to remember. If we have a greater than or equal to, or a less than or equal to, then we're going to have a solid line. If we have a less than or a greater than, but without the equal to, then we're going to have a dashed line. Now the reason we do this is because if it's greater than or equal to, or less than or equal to, then that means that the line itself is part of our solution to our inequality. Whereas in this case, this is just greater than, meaning our line is not part of our solution. So we have to denote that somehow, and a dashed line will tell us that that line is not part of our solution, and a solid line will tell us, yes, in fact, at any point on that line, any point is part of our inequality and part of our solution. So let's look at the problem. The graph of y is greater than 1/2 x plus 3. It's nice that this is in slope-intercept form because we know how to graph things as our slope-intercept form. We can easily graph something in slope-intercept form if we take the y-intercept, which in this case is 3, and so we're going to plot that y-intercept, so 1, 2, 3 right here. And then from there, we're going to use a slope. We're going to use a slope, a rise of 1, and a run of 2. So we're going to go up 1 and over 2 to the right. Up 1 and over 2 to the right. 1, 2. And we're going to make our point right there. Now we could keep going up 1 over 2, up 1 over 2 if we wanted to, but we know that only 2 points are needed to define a line. So with these 2 points, I'm going to go ahead and draw the line. Now, we have to come back and remember that I said that this is a greater than symbol, so it needs to be a dashed line. So I'm just going to go ahead and erase. You could have dashed the line to begin with if you wanted to, but here I'm just going to erase some pieces out of the line. Now, what we want to do is we want to have an area. It's either going to be the down here or up here that's going to be shaded in, because there are more than one solution to this inequality. There are several points that will work for this inequality. If we put a point in, will it give us a true statement or will it give us a false statement? If we have a point that gives us a true statement, then all of those solutions in that area are going to be a true statement. So let's pick a point. I'm going to pick 1, 1 because 1, 1 seems to be an easy enough point for me to kind of figure out what's going on here. So I'm going to plug in 1 into my original inequality and see if that comes out to be a true statement or a false statement. So let's plug in 1 for x and 1 for y. And that gives us that 1 is greater than 3.5. Well, is 1 greater than 3.5? I don't think so. At least not on our planet. So we're going to say that this is a false statement. If it turns out that this is a false statement, then nothing down here is going to be a true statement. None of these points are going to work. So if none of these points work, that means that all of the other points work, and we're going to shade all of the region up on top. Now, to give a better, maybe like a simplistic view of this, if we have our line in slope-intercept form, y equals mx plus b, in this case it's an inequality, y greater than mx plus b, we can just look at the inequality. The inequality is a greater than, meaning all my values have to be greater than this line. Greater than, it's kind of above, right? If I was thinking of something greater than, it would be above where I am. Well, looking at this left to right, if we look at this line, what's above the line? Above the line, y values that are greater than that line are up here. We're going to shade up there. Now that only works if this is in slope-intercept form, y equals mx plus b. So let's take a look at another example. And here I have 2x plus 3y is less than or equal to 6. Now this is in standard form. Now you could graph it straight from standard form if you found the x and y intercepts. But I think that if I want to use this trick above or below the line, I'm going to want to put this in slope-intercept form. So let's go and put in slope-intercept form. Then we'll graph it, and then we'll just use the above or below trick that I talked about in the last one. So we're going to subtract 2x, and we're going to have 3y is less than or equal to negative 2x plus 6. Okay, so I subtracted 2x from both sides of the inequality. Then I'm going to divide everything by 3 to isolate y. And I get y is less than or equal to negative 2/3 x plus 2. All right, so let's graph that. So we're going to go up 2. And then our slope tells us we're going to go down 2 units and over 3 to the right. So down 2 and over 3. And we make another point. Now we don't need to make any more points because we know that a line can be defined by 2 points. So this is a less than or equal to. So we look back over here, and a less than or equal to is here. Solid line. So we're just going to make a solid line between these 2 points. Now what happens? Well, we can use a trick. Let's look at this. Less than or equal to y. Our y values are going to be less than or equal to that entire line. Y values that are less than this line are down here. These y values are less than that line, so I'm going to shade down here. Now, if you want to really check your work, you can use a point. I think the origin is a pretty good point in that area. Let's plug in 0, 0. I'll plug in 0 up here, 0 here. Is 0 less than or equal to 6? Well, yes it is. So we shaded the correct region. All right, you can catch me at Mr. Maestas on YouTube or at Maestas Teacher on Twitter. If you need any more things, go and email me, see if this helps you out. Hope it did. Again, graphing linear inequalities. I'm Mr. Maestas. Catch you later.